the graph of a quadratic function always looks like a parabola. Now let's look at how do we actually find that and how do we do that. And like we talked about in the previous videos from last lecture series, we can always graph a function by point plotting, by hand. We could always use a calculator. There's various ways to do it. With quadratics, it's actually very helpful to first find the vertex as we did. But let's say we didn't know this. Let's just use a calculator to graph, just say h of x as an example. And let's try to look at the properties and the behavior of the graph of h. So go ahead and type it in your calculator. It looks like I already did it. In your y equals menu, type in your function and then hit graph. So if you're looking at my calculator, you can see that I have actually a customized window. I wanted to explain how to use the customized window as well, because it's very, very helpful to do this. If you hit window in your calculator, most graphing calculators will allow you to completely customize what part of the graph you're showing. And this is something that you can tweak, but I just wanted to mention what it means. Xmin and Xmax is basically like, what's the domain? From left to right, which numbers do you want to show? So I have from -5 to 8 programmed just because I chose that. And the XSCL stands for the scale, which just means that they're going to put a tick mark every one number. And usually I suggest to leave it at 1 unless you're looking at a very, very big domain or very, very small. And same for the range. Ymin, Ymax is going to graph, well, what's the bottom of your window, what's the top of your window, and what's the scale again will be how often do you want it to create a tick mark. And notice that when I graph it, that's exactly what it will show, from -5 to 8 and from -2 to 15. And this is really useful because if you ever are trying to recreate a graph or match a graph or something, you can always, and let's say you're given a multiple choice, like is it this graph or this graph or this graph, you can always recreate it by programming in exactly the viewing window based on the domain and range you have. But in this case, I just chose this window. But anyways, when I'm looking at the graph, notice that I get that parabolic shape as it must be. And notice that the vertex occurs at, well, 2 to the right and 1, 2, 3, 4, 5, 6, 7. No coincidence, because when I perform the algebraic process of completing the square, it's always going to put it into vertex form, and the vertex is always apparent from that. But anyways, if we're graphing a quadratic function, one of the reasons why the vertex is so important is because that's a really important point of interest, right? It's like literally either the top or the bottom. In this case, the bottom, the minimum value of the parabola. And it's usually a point that we would like to mark on our graph. 2, 7 is the location of the vertex. And otherwise, it's going to continue to move from there. And since I'm just creating a rough sketch here, I don't need to go too much further. But if we were point plotting, we could also check by plugging 2 into h of x to make sure. Because notice I haven't really verified that that actually does produce 7 for the y value. But if I were to check a h of 2, let's just do it as an exercise, that would give me 2 times 2 squared minus 8 times 2 plus 15. And 2 times 2 times 2 is 8 minus 16 plus 15. And that is indeed -1, 7. So I can tell, but notice that I wouldn't have known that that would necessarily be the vertex if I had not already completed the square or looking at a graph. So my other point is, if you're trying to find the vertex form of a quadratic, another way to do that is to just look at the graph, and it always has to be of the form ax minus h squared plus k. And if you're finding h and k, you can just plug those into the vertex form to write the equation. So it's sort of a backhanded way of finding the vertex form of a quadratic. It's just find the vertex on the graph, plug it in. Cool. And I'm just trying to teach you another way you can find it if you need it to. But actually, there's a couple other things I wanted to talk about when it comes to the graph of a quadratic, just some terms for you. And there's what's called the focus of a parabola, which tells you that, like, if you were to send light rays or sound waves or something into this parabola, it would all reflect to a common point. But we're not going to study it in that great of detail. Usually you go into that if in the chapter on conics, which is actually not part of our curriculum. So not that the focus and something which is called the directives, not that those are not important, but we're just not going to get into those in this class. But what is something that I thought I'd mention is what's called the axis of symmetry. Notice that the parabola, parabolas are always symmetric, meaning they're the same shape on both sides of the vertex. The vertex is always down the middle of the parabola. It's not necessarily the middle of the graph, but from the parabolic side, there is like a central axis. And that's just what we call the axis of symmetry. And the axis of symmetry to a vertical parabola is always a vertical line right down the middle. And we draw it as a dotted line instead because remember that the solid line is always what is our graph, the graph of our function. And a lot of times we have boundary lines or other lines that we draw. Those lines are typically dotted because they're not part of our graph and we want to distinguish them from what is part of the function and to what is not. But we could also write that as an equation. And if you remember, equations of vertical lines are always of the form x equals, which are not functions. But anyways, if you're ever asked, this is usually something I don't focus on too much because I don't think it's that important for this class. But just if you're ever asked for the axis of symmetry, that's one way you can find it. It's always the same as the h. X is equal to h is what you could remember for that location.